Welcome back, my friends, to the show that never ends. We're so glad you could attend. Come inside, come inside. There behind the glass stands a real blade of grass. Be careful as you pass. Move along, move along.
Hi, and welcome to MetalForming Live, where the pages of MetalForming magazine come to life via a three-part online educational event. I'm Brad Kuvin, Editorial Director of MetalForming magazine at the Precision MetalForming Association. And along with PMA President David Klotz, MetalForming publisher Mike Volan, our Senior Editor Lou Kren, and the rest of the PMA and MetalForming magazine team, it is my distinct pleasure to welcome you to this one-of-a-kind event. For 3 consecutive Wednesdays in July, tune in as Lou and I host panel discussions with MetalForming magazine's 3 expert columnists, Pete Ulintz, Danny Schaeffler, and Eren Billur, along with special guest panelists, each experts in the field. These 90-minute roundtable discussions will address 3 topics of critical importance to metal formers: how newer materials such as advanced steels and aluminum grades impact metal formers, simulation of progressive die designs, and optimizing press stroke rate without investing a lot of money. Each of these sessions will feature a brief technical presentation by one of our columnists, followed by lively discussion by our panel, and of course, the panel will address your questions. So please, we invite you to participate and ask questions of our panelists. I want to thank all of you for attending today's session, and of course, thank our sponsors as well. We look forward to seeing you at our remaining sessions as well.
Hi everyone, thanks so much for the opportunity to be here today. My name is Michael Hart. I'm a Senior Director of Product Management with Plex Systems. Plex is proud to sponsor the 3-part series of MetalForming Live. As the metal forming industry continues to evolve, metal stampers and fabricators like you must think outside the box to overcome new challenges and hurdles. Technology solutions, like the ones being discussed during MetalForming Live, are essential to maintaining productive and high-quality operations. In addition to these technologies, Plex Systems' smart manufacturing platform continues to evolve alongside metal formers and fabricators. Plex was born on the plant floor and purpose-built to deliver the total visibility and integrated quality metal formers and fabricators need to support efficient operations, increased throughput, compliance, and cost control. We recognize that manufacturers need to adopt technology in different ways, which is why we recently announced the modularization of the smart manufacturing platform. This approach allows manufacturers like you to build a smart manufacturing technology strategy that focuses on flexibility, quick implementation, and ease of entry into Industry 4.0. We here at Plex hope you enjoyed these live events from MetalForming magazine and the PMA. And we're proud to be supporting the event. Enjoy.
Okay, here we go. MetalForming magazine is live from our newly renovated PMA headquarters for the first of our 3 online events. I'm joined here today by Senior Editor Lou Kren and our distinguished panel of columnists and special guests, all experts in the field. Before we launch into our presentations and panel discussion, I want to thank the sponsors of these events whose generous support makes them possible. Plex Systems, whose welcome remarks you just saw, Delmia Works, Nidec Press and Automation, Pacific Press Technologies, Principal Financial Services, and of course, PMA. Before we get started, just a few notes about today's online event. This meeting is being recorded for archiving, and the recorded event will be posted to our website within the next few days. We'll let you know via email when that recorded session is available for viewing online. Also, all participants in this meeting are in listen-only mode. That means that we and other listeners will not be able to hear any audio from your site during the program. However, you will be able to communicate with us throughout the program by submitting any questions or comments that you might have using that question box, which is located on the control panel of your Zoom screen. You'll use that same question box to also ask questions of our panelists throughout the meeting, and we invite you to ask those questions during the meeting. We want this to be interactive, and we really want your participation. All right, so without further ado, it is my distinct pleasure to turn things over to our Senior Editor, Lou Kren. Lou, take it away.
Thank you, Brad. And thank all of you for joining us for part one of our three-part Metal Forming Live event as we detail newer material grades. Let's start by having our expert panel introduce themselves. Pete.
Welcome, everybody. My name is Peter Ulintz. I'm the technical director here at Precision Metal Forming Association. And for the past 16 years, I've also had the privilege to author the column Tooling by Design in Metal Forming magazine.
Hi, I'm Mike Austin. I'm Director of Manufacturing Engineering for Diversified Tooling Group. We're a large tool and die operation that performs tooling for automotive and other industries. And we also do low volume stamping and assembly. We're located in Michigan.
Hi there, I'm Danny Schaeffler. I'm president of Engineering Quality Solutions, a consulting firm specializing in sheet metal formability. And I am also a columnist for Metal Forming magazine. I write the Metal Matters monthly column.
And now let's meet our online panelists. Steve.
Good afternoon. I'm Steve Young. I'm the stamping engineering manager at Diversified Tooling Group.
And Eren.
Hello, everyone. This is Eren Billur. I'm joining from Turkey. I'm about maybe 10,000 kilometers away. And I have a consulting company called Billur MetalForm with my name. And we do offer simulation, material characterization, and similar. And I'm also a Metal Forming magazine columnist at Cutting Edge for the last 2.5 years. Thank you.
Thank you, panelists. Now it's time to get started with part one of Metal Forming Live. How newer materials, including advanced steels and aluminum grades, impact metal formers. We'll begin with Danny Schaeffler exploring the topic, followed by a panel discussion and Q&A. Then the panel will answer your questions. Let's welcome Dan.
All right, thank you very much, Lou. Yeah, so today we're going to kick off just with a discussion trying to frame what we'll have a roundtable discussion about. I'm going to give an overview of what some of the newer metals are that our audience is working with. I would think that most people in the who are listening in now probably were not around working with the grades available in the 1970s. Except there probably is a good number of those of you in the audience who might have apprenticed under people who first got their start in the industry in the 1970s, when there were really only a handful of grades, characterized either as mild steel, or what was available then was the carbon manganese steels. That's what passed for high strength steels back in the 1970s. In the 1980s, that saw the introduction of high strength low alloy steels. In the HSLA steels that were commercialized, that extended the strength level with not as much of a ductility penalty. Right now, the clicker is actually having problems advancing the slides. All right, there we go. Come the 1990s, there were some other technological advances in steelmaking that also saw, or that allowed for the introduction of the super high formable interstitial free steels, as well as some higher strength options known as Bay Carnival steels or interstitial free high strength steels. We also started to see greater use of stainless steels, either the austenitic stainless steels or the ferritic stainless steels. And also what I'm showing on the left-hand side of the screen are the number of unique steel specifications that were advanced within the automotive industry. Clearly, these grades have many non-automotive applications, and I'm sure many of you are not in the automotive industry, but the number of steel specs, like I said, were shown on the left-hand side. And at the time in the 1990s, there were 65 unique specifications for the grades that were available then. The 2000s saw the initial commercialization and usage of the advanced high-strength steels. These at the time were what's called the first generation advanced high-strength steels, including some grades that are definitely in common use today, primarily the dual-phase steels. In the 2010s, we saw the introduction of both trip and twip steels, each having additional strength and additional formability. You're seeing greater usage of aluminum alloys, the 5000 and 6000 series of aluminum alloys, again, in automotive applications. And today, we have first now the commercialization of the third generation high strength steels with enhanced strength and ductility options. And you see that there are 200, more than 200 different unique steel specifications. What's the rationale to choose from one grade versus another? Well, primarily, no matter the industry, it comes down to 4 categories: safety, emissions, manufacturability, and of course, cost. I want to touch on the primary difference between conventional steels, the mild steels, the high strength low alloy steels. I'm grouping those into conventional grades that many of you have had years of experience working with. First, with these grades, they are absolutely globally available, but the steel makers around the world more or less use the same chemistry and the same mill processing recipe to get these grades. Well, that's really the definition of something that's a commodity. You can swap between suppliers and there'd be subtle differences. There probably are some differences between suppliers, but for the most part, the properties are going to be the same because the steel makers around the world use the same general approach to hit the mild steels and the conventional high strength steels, which do include the HSLA grades. The biggest difference with advanced high strength steels is that the steel makers are constrained by the equipment that they have. There are specifications for advanced high strength steels that have fairly large windows of yield strength, tensile strength range, or tensile strength, elongation, end value, the important properties for forming and formability. But the windows are pretty large, and that lets the steel maker optimize their mill processing and their chemistry to their equipment to achieve those property ranges. So you'll have steel makers from around the world hitting the wide property ranges that are allowed, but they're going to take up different portions of each of those windows. And that's one of the biggest differences with advanced high strength steels. And that applies to any advanced high strength steels from dual phase, some from your basic dual phase steel up to the third generation steels. The microstructure of mild steels and even conventional high strength steels is primarily a phase that's called ferrite. In the advanced high strength steels, we've got ferrite for sure, but also combinations of other phases, martensite, bainite, and retained austenite. For dual phase and trip steels, they are typically applied on parts that are that'll benefit from deep drawing capabilities. They've got some draw depth to them, but we also need the high strength. The dual phase steels, shockingly, maybe according to the name, have 2 phases, dual ferrite and martensite. In dual phase steels, their hardnesses are dramatically different. Ferrite is super soft, martensite is super hard. And that is one of the things that leads to very good elongation or ductility for the strength level. And along with that comes very high end value for both dual phase and trip steels. And where that is really useful is that those properties do wind up on metal certs. We get them from a simple tensile test. So they're on the metal certs and they're key inputs into forming simulation software. Over the years, simulation packages have developed and advanced where when we're talking about drawn parts, they predict formability exceedingly well. So for dual phase and trip steels, that isn't a problem. There's another common, increasingly used type of advanced high strength steel known as complex phase steels. We've got some examples that are shown on the screen now, and you see they're really not deep drawn parts, but what makes these parts unique, where the features, characteristics of complex phase steels are best used, is that we have a cut edge that is expanded. So complex phase steels have really good sheared edge expandability for their strength levels. Substantially better, actually, than dual phase and trip steels. And the reason for that is, well, from the name, complex phase, there's combinations of every metallurgical phase in there, depending on the strength level, depending on the steel maker. But the ferrite, which in dual phase and trip steels is super soft, steelmakers have figured out a way to make that ferrite actually much harder. And so what we have in complex phase steels is a microstructure that is of a more uniform hardness. That leads to higher yield strength at a given tensile strength, but that also helps when trying to expand cut edges. So as shown with the examples that are on the screen now, the complex phase steels are best applied to parts that have the cut edges that are expanded. The unfortunate, I guess, characteristic with that is the typical test used to characterize the metal's ability for cut edge expansion is known as the hole expansion test. And that test rarely winds up on metal certs. On top of that, the mechanism for cut edge expansion in a production environment is much more challenging. And there's only a select few simulation packages that can incorporate that information. And as I just said, they're really difficult to capture all of the potential variables. So the ability to simulate cut edges is, or the expansion of cut edges is much, much more challenging. And as an example, you probably have heard of the old rule of thumb, 10% clearance between the punch and the die. Well, that doesn't always apply anymore. 10% may have been great for mild steels, but for advanced high strength steels, it's not always the best. I'd mentioned the hole expansion test, and that's what the graph that's shown on the left is referencing. And for if this is a complex phase steel that has 1200 megapascal tensile strength, that's around 175 KSI strength. And if you're using a 10% cutting clearance, you're going to be able to expand the hole around 60%. But if you increase your cutting clearance to 15%, you almost double the expandability of that hole. So that 10% cutting clearance isn't always optimized for a given advanced high strength steel. Another example compares dual phase 780, DP 780, or a dual phase steel with 780 megapascal tensile strength. This is taken from 6 suppliers from around the world. DP 780 is not the same everywhere. There are different types of DP 780 that are available. And as I had mentioned earlier, They're made differently within the steel mill. The recipe is going to be different. What I want you to do is take a look at the gray bars, the tallest bars. That's for a machined hole. Now, a machined hole won't have any work hardened areas at the edges of the hole. That's the best possible condition. This is all for DP 780, and the 6 different steel makers that were surveyed, you could see have vastly different performance. We have negated any effect of hole preparation because it's a machined hole. So what we're seeing is the effect of the different microstructures that's available from steel makers around the world with substantially different expandability of the holes. Now you see the vertical scale on the left ranges from nominally, what's the low end? 25% up to as high as 65%. That's for a 780 megapascal strength material. What's that, 120-ish KSI? For a complex phase steel of substantially higher strength, we're not in the 25 to 65% range, even with a sub-optimized cutting clearance. We start off at 60, and we can make it as great as over 100% expandability. That has to do with the microstructure, in spite of it being substantially higher in strength. So with advanced high strength steel, some of the challenges that you undoubtedly are facing are press load and press energy issues, the alignment of your tooling, tool steels and coatings, lubricant strategy, and of course, heat buildup. We're going to be discussing some of these things in our roundtable, but the bulk of these issues comes down to 2 things. One is that we're working with steels of substantially higher strength than what we were using 10 to 15 years ago. The other issue has to do with the microstructure that is unique to each specific steel grade. But it's not just steels that are presenting us with challenges. Aluminum alloys also present their own unique challenges. Now, primarily for metal stamping, we're talking about, for the most part, the 5000 series of aluminum alloys and the 6000 series of aluminum alloys. We're now first starting to see the usage of 7000 series aluminum, but room temperature stamping doesn't really happen with great success. For that, we need what's known as warm forming or hot forming to make the best use of the 7000 series, which leads to the highest strength aluminum alloys. But if you're doing any aluminum stamping, what the biggest thing you want to take away from in terms of cost savings is you must segregate your scrap. Users of steel, you can even say that they've gotten spoiled over the years. No matter what the grade you're using, let it all fall into the scrap chute, go into a big hopper, and all of your scrap, no matter the alloy, can be intermingled, return it to your scrap partner, and they'll be able to recycle it. No issues, no concerns, no loss of properties. With aluminum, the alloying elements that make the 5000 unique from the 6000 series, unique from the 7000 series, the alloying elements that give each of these alloys their unique properties, you can't intermingle them. If you do intermingle them, then you're going to wind up with a paperweight, and you will significantly degrade the value of your scrap. As a matter of fact, Ford, when they first introduced the F-150 in the 2015 model year, they installed a $60 million scrap segregation unit where they were able to keep the scrap stream from each part unique and return it back to their specific mill source. And that is possibly the most significant factor that allowed Ford to use aluminum alloys in a profitable manner. Wouldn't have been able to do so otherwise. As far as usage goes, there's something about aluminum alloys that actually isn't aluminum. And that characteristic is why aluminum doesn't rust. It's also why aluminum is really one of the reasons why aluminum is really difficult to weld. It's also one of the reasons why your tooling might come up with aluminum. And that is because of a sub-microscopically thick layer that is on the top of every sheet aluminum product that you buy. It's a layer of aluminum oxide. That aluminum oxide protects the surface from rusting, but aluminum oxide melts at a significantly higher temperature than steel, and it's a much higher temperature than aluminum. We need to break through that aluminum oxide when we weld. But aluminum oxide, that's on the surface of every sheet aluminum alloy that's out there. Aluminum oxide is also what makes up grinding wheels and sandpaper, which is why aluminum is such a bear on your tools. Nothing we're going to be able to do about that, but knowing that allows us to put in some countermeasures. There's a lot of successful sheet aluminum stamping that's throughout the world today. I'd mentioned the 6000 series of aluminum, the 5000, 6000, 7000 series. That's how they're grouped, but there are so many options within each of those families of alloys. There are two, I'm showing the offerings from two of the aluminum suppliers, major aluminum suppliers that are out there. And this is just highlighting some of their 6000 alloys that are available. Each of these alloys have different characteristics. Some are tuned for appropriate use for surface panels or exposed materials. Others are tuned for body structures. You might have some that have enhanced bending characteristics. But if you're just ordering to a generic 6000 specification, you don't know which one of these you're going to get. Or you may get one of them, may perform fine, but you may choose to switch suppliers for purchasing reasons. Let's go to the why would we want to spend for one supplier, we can get something cheaper. Just remember, they're going to have different characteristics. That same thing is what applies to the advanced high strength steels. Be careful when you switch suppliers. So with that, I can turn it over to Brad and we can start our roundtable discussion.
Outstanding. Thank you, Danny.
My
We covered
pleasure.
a lot of ground there. A lot going on with these new materials. We do have one question from the audience already on the cost of complex phase steels compared to dual phase for the same relative strength level. Do you have a feel for the cost difference between?
That anything in terms of cost differences, it's all up to the strategies of each different steel maker. First they have to have the capability to achieve the complex microstructures, but once they do, it just becomes a strategy as to how the steel maker wants to allocate their production time. So can't really speak much toward cost of the alloys. I will say though, typically you will find trip steels at a higher cost because they take more alloying elements. The alloying elements that go into trip steels are costlier. They require tighter process controls at the steel maker, and that's going to translate to a higher cost product. For complex phase steels, it comes down more so to the processing. And like I said, that becomes more of a company to company strategy. Thank you for that question. And again, I also want to encourage everyone who's attending, please ask these questions. We love talking about these issues and definitely encourage you to continue to submit your questions.
Great.
Thank you, Brett.
Mike, you don't have any input on the price of these grades?
Not really. I think the pricing is something that depends a great deal on who you are and how much you're buying and from whom. As Danny said, the materials a part of that, but the distribution costs, processing costs, all add into what a typical purchase price is.
Good, thank you. Maybe this is for you as well, Mike. Another question from our online viewers. How often should high volume stampers lab test new coils of steel or aluminum? Any of you guys?
Well, I think that, lab testing is always recommended, obviously with more common steels that are in use regularly, people will cut back on their tests. But in the case of newer steels, especially if they're not being used in high volumes yet, you're going to want to check a lot of those certs out and make sure that the materials coming in as specified.
I also want to add a few things to that. I think it is a very wise idea to run testing, especially during your tool and die development stage, because mill certs, any grade of any alloy, they're obtained from either the head of the coil or the tail end of the coil. And the coil might be a mile long, depending on the thickness. And while the properties throughout the coil will fall within the allowed tolerance band of the particular alloy, the coil end test is not saying that those properties are the same throughout the coil. So when you're doing die development work, you may not be getting your samples all from the head end or the tail end of the coil, especially when we're going to take those properties and put those into the metal forming simulation. So we want to be sure we're capturing the exact properties of the portion of the coil that we're running during development. Now, as Mike said, though, it's probably a wise idea for advanced high strength steels for now to run at least periodic checks, because overall, hundreds of thousands of, if not more, HSLA coils have been produced. So steelmakers really do know their processing recipe and have locked it in pretty well. But that's not always the case for some of the advanced grades. Maybe with DP600, that has been the workhorse. But when we start getting into even higher strength dual phase grades or other advanced high strength steels, steelmakers don't have as large of a processing history. So it couldn't hurt to confirm what you're seeing. And if you're seeing that the mill cert actually does replicate what you're getting, and you're testing from the body of the coil, let's say, then that's fine. You can stop the testing. But short of that, you do want to confirm that the property variation you're seeing is that your process can handle that property variation.
Yeah, I'll echo Danny's point regarding the center of the coil. You definitely want to try out your tooling and go through complete coils. It may cause you to buy 30 or 40,000 pounds of material instead of 10,000, but you're really going to want to experience full coil in your tool tryout. But from a tool maker perspective, we want to see that because we don't want to see something different when we go to home line.
And keep in mind the relative cost of the hours of that are being put in, just the amount of time that you're putting in, the cost of a coil, and worse yet, if you're running into production problems, you want to be sure that you don't want to start playing with your tooling to make a given coil work because you think that coil is within spec. Or maybe it's within spec and it's at the very high end or the very low end. Before you put the grinder to the tools, spend a couple $100. confirm you know what the metal is, and then make the decision whether it's worth getting that coil to run. Don't trust the metal cert when it comes to that.
May I comment in here as well?
Go ahead, Eren.
What I have seen, I'm totally agreeing with Danny, first of all, but even at mild steels, which has been around for many years, we still have a lot of variation. I don't know how it's in the US, but at least in Europe, this is very common that sometimes you buy a CR3, I think that's called like deep draw steel, but in fact, you get an extra deep draw steel, the higher quality, for the same price. That's because of commercial reasons. And if you check the spec sheets, CR3, as we call in Europe, every CR4, you can sell them as CR3. Or every CR4, which is the more expensive one, you can sell it as CR1. And what happens is, when you start the buy-off or the starting of the production, if you get a very good CR1, which is commercial steel, in reality it's a deep draw steel, but you bought it as commercial steel, everything works very fine. And then you get a real commercial steel that would not be eligible to be called as draw quality steel. Then you get a lot of troubles. Same thing applies with HSLA. Most of the specs, I have seen, we do a lot of lab testing, by the way. I have seen a steel that was sold as HSLA 340, but it was at the very high end, and it could be sold as 380 or 420. So in HSLA, you can see that there are some ranges that one steel could be called all three. And sometimes you buy it as 420, sometimes you buy it as 340. So what I would suggest is, especially when you are, is it called maturing the die, when you're getting it into production, you should really know what material you had at that time. And every time the mill certificates, I agree with Danny, they're not the best, but they're the cheapest to check. I mean, you don't spend any pennies to read that document, and that should give you at least some ideas, although it may not be always the perfect one. And answering the question about how often, I would at least say a few points here. Number one, if you have never made a part, for example, this is Martin Stick 1500. If you have never stamped a part out of Martin Stick 1500, and if it's your first time, do a lab testing. And if you are switching from a major supplier to another one, and especially like, I don't want to give any names here, but from a European one to an Asian one, let's say, that's a big change most of the time. That's where I would suggest making a lab test. And also, if you are using the same nominal name, let's say DP600, that's a nominal name. But if you are buying it according to some WSS or GMW or FCA or whatever, you have to be careful that they're not equal. They're similar, but they're not equal. Thank you very much.
Thanks, Eren. Thank you.
I'd like to add one more point on that subject. Most people look at procuring their tryout material for the needs of the tryout operation for the tooling. But if you buy excess material, that material is not going to go to waste. You're not going to scrap it. You can plus it out. You can cut your sheets long and large and still use that material for initial production. So it's just a little bit of acceleration of some material costs that can save you a lot of trouble down the road.
Okay, so in terms of stamping these Gen 3 steels that Danny so well described, Mike, can you tell us a little bit about what you found at your company that you need to do differently regarding die design and build in order to stamp these steels?
Well, the higher strength steels, when you start migrating from 500 megapascal to 1,000 or 1,500, you're going to see all of your loads go up significantly. So your die in general has to be substantially stronger, along with your press and your coil feed and everything else that goes along with it. So you're going to be upsizing things, but you're going to be changing the type of construction, the materials you use in your die. There's a lot of factors to take into account. One of them is heat buildup. And as Danny mentioned earlier, when you put more force into making a part, you're going to create more friction, you're going to create more heat, and so you're going to start heating the tool, and that heat can have an impact on it. But there's a lot of different factors that you need to take into account through the simulation, the design, the construction, the tryout. I'll let my associate, Steve Young, talk more about this.
Yeah, thank you, Mike. Yeah, I've listed a few key items here to consider in order to improve tool performance and minimize wear on the tools themselves. Starting with the balance the operation in order to aid in offsetting thrust conditions. You can see in the graphic below, that's a simple example of a balanced trim process. This eliminates, undue thrust in any particular direction if your process is balanced out. Next is employee higher strength casting bar stock materials. This ensures longer longevity and increases tool robustness. Consider high strength material applications as high volume tools. Several of the OEMs have this as a standard practice in their high volume tools. Let's say they're Class A tools, they automatically upgrade casting materials, add double wear plates and backup for trim and flange operations, for example. Inserting draw dies for maintenance and wear, mainly the binder in the cavity to protect the draw beads against wear. And also implementing stake beads to add and reducing curl and spring back as required by the part geometry, the hat section and steep walls, for example. The stake beads play a major role in reducing that curl and spring back.
Steve, one question on your first point about balancing operations. Not only do you need to balance within the die itself, but from station to station on a transfer press or a product die press, isn't it also more important to balance those loads out and get them centered up under the press ramp?
Yeah, absolutely, for sure. That that ensures long-term lasting of the press itself. If you have 3 dies on a single slide and you have the draw die on one side, you need to offset that tonnage on the other side of the press. So you'd add cylinders, let's say, to the third operation to take up some of that offset tonnage.
Good.
On the inserts, I've seen some examples where usually it's advised that those inserts are coated with some type of hard coating, and I've seen that, of course, there are different options for the ways the coating can be applied: thermal diffusion, chemical vapor deposition, and physical vapor deposition, or PVD. I've seen good practice evolve to use PVD because that results in the least distortion of the tools. Chemical vapor deposition and thermal diffusion are both higher temperature applications. But that's just what I've seen and read. I don't know if that's something you've got some direct experience in.
I'd like to comment on that. So when we're looking at inserts on tooling, especially for these high strength applications, especially if you're running in progressive dies where you have a lot more vibration and heat that's being generated, we're looking for tools that are going to be wear resistant and have adequate toughness, and in most cases require a coating. So that's going to change our approach to our traditional view of tool steels. In these instances, you're going to be wanting to look at high-speed tool steels or powdered metallurgy PM tool steels, because these tool steels temper at a much higher temperature than A2 and D2 that we're typically used to working with. And this is what's going to fall in line with the PVD coatings, because these PVD coatings are applied at around 900, 950 degrees Fahrenheit, which is below the tempering temperature. Now, if you use an A2 or a D2, which tempers at like 550 degrees Fahrenheit, when you apply the PVD coating, it's actually going to make the tool softer. So tool steel selection becomes really important when we're looking at inserting dies for high strength applications.
Yeah, and on that subject, Steve, is there, as you migrate up to higher strength tool steels, does that take you out of the cast world, you know, where a lot of conventional steels are cast? Do you have to go with bar stock?
As far as the inserts, is that what you're asking?
No, for, let's say for a trim steel or something, can you get a cast cal die trim steel?
Yeah, you can get there. You know, there's still a cost hit between conventional casting and cast cal die, but you can get cast Carmo, and you can get there are definitely different material options for those that are you know, increased strength over typical gray iron casting, for instance.
Good. Thank you. Steve, I know you had a little bit more to share with us on spring back, and as your last bullet point there, you want to talk a little bit more about managing spring back?
Sure.
Yeah.
So this is an example of the introduction of a stake bead in a draw operation. This has helped us considerably reduce curl and spring back in some of these higher strength parts. In the screenshot you see on the left, that's this is the draw off bottom. You can see the conventional bead geometry in the, let's say, the downward direction. And then just to the left of that is the introduction of a stake bead. So this is 5 millimeters off bottom. The green geometry on the bottom there is the stake bead itself. That would be a detail that's through the lower binder and mounted solid to the lower shoe or lower punch. And then at the right, on the right, that's the die closed. The stake bead is entered, is finished entering. In this instance, it's 5 millimeters, but that 5 millimeter introduction of the stake bead at the bottom of the stroke, you know, performs a last minute tug on this vertical wall as it's being formed in the draw. So if we go to the next slide. Yep. On the left is the result of a conventional draw operation. That's just a conventional bead. This is a final spring back analysis. This is actually done in autoform. And you can see the curl, the resultant curl along that vertical wall. And then on the right is the addition of a stake bead process in the draw. You can see the reduction, the difference in the amount of curl. That yellow line represents a straight line. Both of these were performed in autoform, and we have pretty solid correlation between these results and some test tools that we've built at Diversified Tooling, and some actual production tools as well. So you can see the benefits of using something like a stake bead in your process.
Yeah, I know that you know, some of the tools we've been running with 980 Gen 3 and 1180 Gen 3 have been very successful using the stake bead. You showed in the previous slide a three-piece tool. Can you do this most of the time with a three-piece, or do you have to go to a four-piece sometimes?
Occasionally, you'll have to go to a 4-piece, it's geometry dependent. For the most part, we've been implementing this in, conventional 3-piece stretch draws, but you could use this in a 4-piece.
Steve, may I have a quick question?
Go ahead, Eren.
Yep.
I was going to ask you the material card you were using, and then I also saw there's also a question. What kind of a material card you were using in AutoForm with this one? Was that through a supplier, steel supplier, or an OEM, or did you do it yourself?
This particular example was from the steel supplier. Yeah.
Okay, because especially for swing back analysis, and again, that's in hand with the question we received from Ajay Gupta, Mr. Gupta. You need to take into account the kinematic hardening, which is very hard experimentally to get that data in. It's not impossible, we do that, but it takes a long time, because without that implementation, you have a lot of bending, unbending, rebending, unbending, and rebending. It's very hard to predict and correlate that with reality without taking that material data in the material cards. So if it's correlating very well, I can guess which steel mill you get this data from.
Yep.
Okay.
So, yeah, there's a question related online. And so is the wall curl simulation, I guess this is for Steve or Mike, is the wall curl simulation considering the kinematic hardening model? I don't know, is that for you, Steve, maybe?
Yeah, in this case it is, yes.
Good. Thank you. Okay.
Can you go back one slide? Thank you. I can see on the previous slide, one of the downsides to using a stake bead approach is that you're going to need a slightly larger blank so you could get enough real estate to have both your draw bead and the stake bead. Are there other downsides or challenges or things that users should be aware of when they go to a stake bead approach to minimize spring back?
Yeah, it adds to complexity of the die. Obviously, when you introduce the stake bead, you're introducing that additional detail. Typically, when we have a stake bead process like this, or that stake, in order to be able to, tune this in, you might go 5 millimeters, you might go 5.5 millimeters. It depends on where you get in tryout. There's some machining complexity involved with the lower binder itself. You have to create this, this slot that allows the shape set to move up and down in, and you have to be able to somehow back up that shape set detail to the binder, because as you can imagine here, there's going to be a lot of thrust on that bead detail. So maintenance, yeah, there's some cost machining and a little added complexity to the die itself.
Steve, one more question on stake bead. Doesn't the stake bead cost a lot in terms of tonnage? What type of tonnage increase do we see when we use a stake bead?
As far as a percentage, we generally see maybe a 20% increase at the bottom of the stroke in terms of overall tonnage. If we ran it without versus with, there's a pretty significant hit at the bottom of the stroke.
Which is usually not too difficult to get out of the press, because that's where the press has its most tonnage.
Yeah. Yep.
So it's usually not too big of an issue. It's not like you're setting a bead high up in the stroke where you don't have tonnage available.
Right. This is where the press is at its highest. So.
Okay, good. We have a question online I want to go ahead and address before we get too far in. The question is, how can you best explain the difference in HER for a complex phase steel at a 10% clearance versus 15% clearance. Is this a relatively small difference in breakage for that outcome? I don't know, best to.
That's HER is the whole expansion ratio, if I may.
Go back to your-
Yeah, if we can go back to the slides, please.
We anticipated this, right?
Let's see how well we can do all sorts of things technically, but put us in front of some
Yep, you're in.
technological issues here. All right. So the question was related to whole expansion ratio, or HER. That's on the vertical axis. And the difference between why 10% clearance isn't optimized. I believe a lot of it has to do with the work hardening, the damage that's put on the edges when the material is cut in the first place. You're changing the ratio of rollover, break, fracture, and with 15%, you're for these higher strength grades, you might be doing less damage. Now, also keep in mind, this isn't saying that 15% is the ideal clearance for all advanced high strength steels. It's for this particular grade, maybe, probably even from this particular supplier. So as you're doing your tool development, you want to know for each grade, once you've locked in your supplier, you want to know what those capabilities are.
Yeah, I'd like to comment a little bit on cutting clearance as well. Typically, what we see, if you think about cutting clearance in your die, the reason we have cutting clearance is that clearance acts as a lever to bend the slug so it breaks out of the material. Now, just think if you needed to move something with a lever, okay, and you have a lever of a given length. Now, if you have a larger mass to move, or in this instance, a higher strength material, you need a longer lever in order to cause that to move or bend. So typically what we see in general with higher strength materials is we need to have a larger cutting clearance so we can bend that slug so it breaks out of the material properly.
Great explanation. Thank you.
I'd like to add our experience in doing some R&D on some 980 Gen 3 materials is that, you know, the clearance that we need for supplier A is going to be different, quite a bit different than the clearance that we need for supplier B. And the same is true in the results we get from the material and its susceptibility to edge fracture. And the clearances that you're using for trim are certainly going to be a lot different than what you're using for pierce.
Also, you want to keep in mind the magnitude of what we're talking about. The difference between what is 10% versus 15%. Well, we're in the few thousandths at best for the typical sheet metal thicknesses that we're working with. And so it doesn't take much to tip you from optimized to sub-optimized. And the numbers that we're showing here, the 10%, 15% of sheet metal thickness, that's an idealized condition. Maybe you're perfect at 15% when you are doing your tool development. But then if you're putting it into a press that is several decades old, maybe there's some slop in the system. Maybe what you have started off in your tryout press as a perfectly centered hole where the punch is perfectly centered in where you want it to be. Well, if it's not, once you get into production, you may start seeing fractures because one side of your hole is going to be below 10% clearance. It's tight on one side, and you'll have 20+% clearance on the other side, just because of alignment issues. So when you're doing your troubleshooting, you actually do want to look, where does that fracture occur? If it's consistently on one side of a punched hole, maybe that is telling you that it's an alignment issue. Could be something with the material too. But capturing that information does help in your problem solving.
Yeah, and obviously you're going to want to share your trim steels and your pierce punches. And as you do that, it's going to cause side loads on those steels that will have an impact on your clearances, and that has to be taken into account.
And that loading is even higher because we're talking about higher
Big
strength.
load.
Yes.
Good. I want to go back to the stake. So we just have a general comment on stake beads, and you may or may not have further comment on this or agree or disagree. The person in the audience says the stake bead needs to be on the punch inside the punch opening line and outside the trim line. That's not right.
Steve, you want to answer that one?
Yeah, that's true. Needs to be inside the punch opening and also the trim line. I mean, it's all out on the addenda.
All right, so kind of a general question. All of you guys could probably answer this one. Maybe Pete, you could start on the difference between elongation and value.
I think that's maybe more mine.
Is that you? Okay.
That is maybe
Go ahead,
more
Dan.
mine. They absolutely trend in the same direction, but there is absolutely no correlation between the two.
Okay.
Or there is a correlation, but it's not a good one. So it is from the way the steel hardens. That's why if you just get a YTE, if you just get yield, tensile, and elongation, you can't plug that into your simulation and hope to get accurate results. N value is a critical component of sheet metal form, of at least steel formability. It's actually not as strong of a driver when it comes to sheet aluminum alloys. But N value is a standalone separate parameter that tracks with elongation, but not well enough where you could just use elongation as a substitute.
While we're on that subject, Danny, you might also want to comment on with the advanced high strength steels, another concern besides elongation or global elongation is we have to be concerned about local elongations become much more of a concern than in mild steels.
Absolutely, absolutely. And that is something that I alluded to when showing the slides having to do with dual phase and trip steels, which have very good elongation and N value. But complex phase steels have what's known as local formability or cut edge extension. So they're measuring, the tensile test is really good for what it is. It's uniaxial tensile loading, but that does not capture all ways that sheet metal stampings can fail. And that's where you would benefit from having the hole expansion numbers to characterize the difference in cut edge expansion.
And
also,
go ahead.
oh, sorry, Pete. Sorry, Pete, you can go ahead.
Hi there.
Shall I continue? Okay, so I had a few comments about elongation and N value. First of all, there are a number of different elongations. The simplest difference is uniform elongation and total elongation. For most steels, N value and uniform elongation are hand in hand. But the problem is we typically see total elongation in the mill search, and there is a difference in total elongation. In Europe, this is the tensile specimen that we use. This is 20 millimeter wide, and the gauge length is 80 millimeters. In the US, you use a different one. And if we cut same steel with the ASTM E8 versus Euronorm 6892 versus Japanese, we would get different elongation values. And you can clearly see this in global OEMs. They have 3 different elongation numbers for total elongation. But N value, especially for most steels, it's very agreeing with the uniform elongation, but has no idea and no correlation between the total elongation. And again, total elongation is something we have to be very careful with. A50, A80, A50 type 1, A50 type 3, they're all different.
Very good. You covered.
My comment, Danny, with regard to dual phase steels. So we started out with having the original Gen 1 dual phase steels, and now we have these Gen 3 dual phase steels. So if I'm working with a customer and in discussion, we want to produce this out of a DP600, how do I know if they want a Gen 1 steel or a Gen 3 steel? How do we know we're talking about the same thing? And it's kind of a two-part question. And then as a supplier, if I have problems with a Gen 1 steel, a DP600, can I go to a Gen 3 to capture that additional formability?
Okay, so that's a complex question, like a complex phase, but that's okay, because there aren't straightforward answers. One thing to keep in mind, although DP600 isn't a great example, we go to DP800. That 800 tells you what the tensile strength is. It doesn't tell you anything about the yield strength. And there are commercially available DP800s that have a minimum yield of 420, 500, and 550. They will all have 800 megapascal minimum tensile strength, but they're designed for different things. If you want drawability, you want the lowest yield strength version. That's going to be something that will, like I said, give you the highest elongation associated with that. That would be from what you had just mentioned, global elongation. And that, like I said, is for deep drawing. If you have the highest yield strength version of the DP800, that's going to be good for your cut edge expansion. Because of the modifications in the microstructure that gets you that high yield strength, that's what's going to keep the microstructural phases of a similar hardness, and that's what's going to lead to the best cut edge expansion. So if you're just ordering to DP800, your steel supplier will give you something that meets that minimum tensile strength. But they may be giving you a version that, well, your first supplier may give you a version that's perfect for the needs of your part. You switch suppliers, you want to be sure you're getting that same version of the DP800 because around the world, there are commercially different options. And so first you would need to, if I can address the second part of your question, you need to define how and where the stamping is failing. Is it failing at a cut edge? Well, that tells you you want to be sure you can order the highest yield strength version of that DP800 grade. Or is it necking failure as you're doing a deep drawn part? And metal stampers have dealt with necking failure as the primary failure mode for decades. If it's going to produce a smile or a reduced thickness in one area, it's called a neck. That's where you want the lowest yield strength version. It's an option certainly to go to a third generation steel that has enhanced formability in total elongation. That's probably not going to be your best option overall. It's certainly a consideration, but it's going to be a higher cost product. There are fewer and fewer, at least for now, companies that make third generation steels. So there's going to be potentially a cost and a supply base issue. It may be better to attack where the failure is coming from, and while keeping the metal the same, do changes to either the tooling or the die process to get you to that point. Thank you, Pete.
Let me change directions for just a second. We talked a lot about steels. You talked about the 5,000, 6,000, 7,000 evolution in aluminum alloys.
Yes.
What do we know about the need to change the stamping lubricant when we move amongst those series of aluminum alloys?
Within the aluminum once you're in aluminum, typically you can stay within the same lubricant or type of lubricant that you're using. If you're having problems forming, well, certainly dry lube is a very common option, which is going to be a barrier approach between the tooling and the aluminum surface. And that is used in high volume automotive applications by many stampers of sheet aluminum alloys. But that lubricant you use for aluminum almost certainly needs to be a different lubricant than what you would use for sheet steels.
Is there a recommended, actually the specific question was, is there a recommended for aluminum? And I know that might be.
I would absolutely suggest you talk to your lubricant supplier and see what they recommend, because not all lubricant suppliers are the same, have the same offerings, and just like your strategies have evolved as you go from mild steels to HSLA steels to advanced high strength steels and to aluminum, lubricant suppliers have gone through that same evolution. And tool steel suppliers, they are optimizing their products to help best form and process these newer alloys.
Yeah, on that subject, lubricants for aluminum tend to be a little fussier from our experience than for steel, especially if you're doing Class A exposed aluminum. You're going to have a lot of issues that you don't have with other materials, and you also have the aluminum oxide to deal with in your tooling. So most of the customers that we have doing Class A exposed aluminum are using a dry lube that's specifically for aluminum and selected and approved by the OEM or the tier 1 or tier 2 supplier to provide the lubricity that's required, but also is capable of being cleaned and welded and provides the corrosion protection required, because there's a lot of unique issues with aluminum that you don't have with steel.
And not to say that aluminum alloys can't be processed. You just need to change up a few things. Your practices need to be in line with the characteristics of that sheet metal.
We still got some time left in our session today, and certainly encourage more questions and correspondence from our online guests. So we've got a lot of expertise here on the panel. Please ask your questions of these guys. Question is for those stampers who buy their steel from service centers. They may not have the volume for a mill direct buy. Is there anything they should be aware of when they're speccing their steels, receiving their material from the service centers, et cetera?
I think that you want to be sure you're asking for what you need. So just specify yield and tensile strength for sure, and of course elongation. Don't just call it DP 800. Put in the characteristics of what you need, because steel makers will make those products differently from source to source, even within the same company. If a steelmaker has multiple locations that may have been built at different times, they have different equipment. Each type of equipment has different characteristics, which the mill location has optimized, but it may be different than its sister company, 3 states away.
Mike, are you guys buying direct or you buying?
Well, we do both. We do a lot of die tryout. And of course, for that, we're normally getting pre-sourced material either from the mill or in some cases through distributors, and in which case we have to be very careful about the material we get being representative of the material used for production. But we do a lot of low volume stamping as well. And in those cases, we mix between mill purchases and distributor service center purchases. And there's a lot of challenges as you switch between those. It's a different way of doing business and you get considerably different results. We're also involved in, as we do volume production, we get involved in resourcing material, especially with some of the material supply chain issues that we've seen recently. And as we noted earlier, you want to be cautious as you look at a resource and you change materials, that you do a thorough evaluation of the new material, regardless of the specifications.
Thank you. So you talked about the fact that you guys do a lot of prototype development. Do you see any trends to avoid building prototyping tools and just rely on simulation? And should this change, with this movement to these more advanced material grade?
Well, from the day that people started using simulation, everyone predicted the demise of prototyping. It has not happened yet, but we do see a significant trend taking place where people are pulling ahead parts from their production tools, and they concentrate on getting the draw dies and the forming dies, the flanging dies built early, and then take those parts and laser trim and pierce to get some early parts and try to use those for prototype. That's largely driven by cost and also the desire to compress timing. However, if your tools are not coming from a local supplier, you may be a little bit at risk for timing on when you're going to be able to get those parts and those tools, because all the timing's kind of been up in the air recently. However, when you look at new materials, if it's not a material that you have a lot of experience using and a lot of history, you really should look at an inexpensive prototype tool just to gain experience with the material. And in some cases, you can even use prototype level tooling with production intent to be able to make early parts instead of forcing your production tool to try to provide those early parts. And so we see a lot of strategies that people have successfully implemented that way, especially if they're not sure about their trim lines or their hole locations. They postpone getting those hard tools cut and use laser in the interim, or in some cases for form tools, they'll use a soft tool or a low grade production tool to satisfy initial panel requirements.
Yeah, and the risk there, because there's a risk associated with that, especially if you're looking in terms of formability in your process. With soft tooling, the compressive strength of the tooling is going to be less, frictional conditions are going to be different. So I would not advise, I wonder if you agree, trying to develop trim edges and things like that in a soft tool.
No, you really need production intent tooling with comparable tool qualities where you can compromise and do some of your draw tools and your form tools. You can cut back on the materials and also on the construction. And you may only work on a certain area of a part. Maybe the majority of the part's fairly straightforward. You can build a tool in one small section of a part and prove out the material and die process by doing that without spending a lot of money.
You had mentioned, and this is typical, the last tool that is built is usually the blanking die. So typical practice might be to use laser cut blanks during tryout. That may have worked well in the past, but the caution is a laser cut edge is not going to behave the same as a sheared edge that you get in production. Again, mild steels, maybe not an issue. But when we're talking about advanced high strength steels, especially if we're talking about dual phase steels, the cut edge quality in shearing, well, we've seen it was different between 10 and 15%, substantially different when you're comparing that with a laser cut edge. So your initial blanks that you're forming, if your part has a cut edge, pierced edge that's expanded, laser cut blanks won't give you that a good representation.
Well, that's an excellent point, because with laser blanking, you're going to be able to produce an edge quality that's far less susceptible to edge cracking, and your holes are less susceptible to fracture. And in fact, that's kind of driving a lot of people towards the use of lasers blanking from coil. We're starting to see that become far more popular because the production rates have gone up, the number of installations have gone up, and especially with advanced high strength steels, as well as some of the aluminums, you're able to get comparable costs today on certain types of panels coming out of laser blanking.
And PMA very recently PMA and Metal Forming magazine put on a webinar on laser blanking. Excellent webinar if you haven't already viewed it. But one of the other caveats, because the question initially was eliminating prototype tooling. Relying on your simulation to predict press loads isn't always the best move, because if you're incorporating strategies like stake beams to control spring back, that may or may not be in your simulation. So the ability to accurately predict press loads just from simulation is great if you consider all of the factors that are going to be involved in production, but you may wind up underestimating it if you don't include things like stake beams.
Yeah, I think a lot of the simulations with the second gen as well as some of the third gen steels have under-predicted tonnages because of the work hardening taking place, and that continues to be a problem. So as you use these higher tonnage steels, you need more safety factor.
Yes. Yeah. And speaking of the work hardening, if in the image we had about stake bead usage, where we had draw beads outboard of the stake beads, as the sheet metal is going through the draw beads, you're work hardening them. You're work hardening the material. So when that metal hits the stake bead, it isn't the virgin steel that comes out of the steel mill. You need to incorporate the work hardening of the bending and unbending through the draw beads, and as well as the extra tonnage from the stake beads when you're doing your simulation, to let you know if your press is going to have enough load to set all beads and to control metal flow.
Yeah, and setting up beads is one of the things where doing a small sample of a tool and building your bead up and doing tests in that with a new material would be a wise thing to do before you build a big tool.
Sure.
And so you mentioned the laser blanking technology for this application, and we did do a webinar on that subject last week, which is up on our website if anybody hasn't seen it yet. Is laser blanking something that you guys are looking at, Mike? Are you doing laser blanking for these materials? Or
We use a couple of sources for laser blanking today, primarily for some of our PHS low volume stamping, as well as some of our higher volume full stamping work. It's fairly cost effective. The industry is really maturing right now, and we're starting to see pretty rapid adoption of the process, especially as people recognize that they can make these blanks at comparable costs and help resolve problems with edge fracture.
yeah, so this is an interesting question we have from our audience. I think, Pete, with your experience in the industry and Mike's company as well, is it necessary as a stamper to evolve with these new materials to learn how to handle these types of steels? Or does it just depend on the industry you're in, and you can, how do you make those decisions to try to keep up with all of this? Mike, we were talking earlier about the increased press tonnage that's needed. Some of these presses that were bought less than 10 years ago are now starting to become obsolete with these steels. I mean, and maybe these are decisions that are made at the higher levels of these companies, but what's the pressure that you feel to kind of keep up?
My comment generally is in my seminars and that is to not ignore these materials, especially the dual phase materials. You may not be producing automotive components or body in white structures right now. And a lot of times the attitude is these new advanced high strength steels, they're automotive steels, we don't have to deal with them. Well, back in the 1970s, high strength low alloy was an automotive grade steel, and it's being used everywhere. And I think we're going to see that, especially with the dual phase steels. I think we're going to see a proliferation through many industries using these materials. So don't ignore them just because you're not an automotive supplier. At some point in time, you will have to deal with them.
Yeah, we're seeing a lot of customers migrate from HSLA up to higher strength materials right now outside of the automotive market, in off-road and construction. Just about every manufacturer of steel products is looking at advanced materials today that are matured in the automotive market. How can they use them in their products?
Yep. And as you go up higher in strength, many applications will allow you to cut back a little bit on thickness. Many applications, not just automotive, are sensitive to the weight. By going a little bit higher in strength, you'll be able to save a little bit of weight because you'll be able to use slightly thinner gauge.
Just a couple more minutes and we'll wrap things up, but this is a good question. I'm not sure which of you wants to field this on press bed rigidity. Not everybody has, and 1,000th deflection, press bed.
Well, I mean, I can answer part of that, and Pete, maybe you can handle the rest, but the typical presses were built with relatively flexible beds and slides. What was it, a 0.5 foot or something was the standard back in the 60s.
Actually, 2,000s per foot.
Okay, well, 0.5 is what you need to be thinking about today. And so the presses that we've been putting in have been stiff bed for that reason, because we know that deflection is a big issue for tooling. It really has a major impact on the tool. Obviously, when we build a tool, we're trying to emulate the home line press. And so we try to find out what those press specifications are and make sure that when we try out the tool, it's in a similar press. But it's very important in some of the large tools. I think as you move down to size, it becomes more important, maybe with your smaller parts.
Yes, and the issue you'll run into as you get into smaller parts, we tend to run those in progressive dies, and these progressive dies can generate considerable off-center loading in the tools. And not only does the bed of the press need to be more rigid, as well as the slide. A lot of press manufacturers over the past decade have redesigned their crowns because breaking of the press crown, it was very common when these dual phase steels first hit the market, and it was primarily because of, if you're doing blanking operations, there is a lot of reverse tonnage that's being generated, and it was just damaging the presses. So newer presses tend to have redesigned crowns. The manufacturers have taken into consideration that some of these advanced high strength steels are going to be run through these machines, and so a newer machine will likely perform better than older machines.
Yeah, and you want to make sure that you're not just focused on getting your tonnage balanced out across the width of the press and under your connections and things, because and taking into account reverse tonnage, but you also have to take into account your cushions. And if a lot of people are not able, especially in a transfer of product, to use a press cushion effectively because of offset loads. So they go with nitro cushions, and with nitrogen cushions, you start building up pressure high in the curve, and now you have a real issue that you have to seriously evaluate. As your tonnage goes up to make a Gen 3 part, your cushion tonnage also goes up proportionally. And so, you know, the cushions in your presses probably aren't heavy enough, and you're going to start adding more nitro and more nitro and more nitro, and all of that's going to have a big impact on your press.
And the other thing with balancing loads, it's not just a numeric value in terms of I'm generating a given load on the left-hand side of the press versus the right-hand side of the press. The other thing that becomes important is, when do those loads occur? In deep drawing, you may have very high loads early in the stroke, and then during your cutting and trimming operations, that occurs at the very bottom of the stroke. So even though the loads are the same, they're occurring at different times. And so you still have this tremendous tipping moment that is occurring.
And then you'll also need to take into account press energy in your flywheel and everything else, because you're doing a lot more work.
So we're going to take one last question, and only because it really kind of leads us to next week's Metal Forming Live webinar on design and simulation. What do stampers need to be aware of when running simulations on these new materials? Are the generic material cards accurate enough to model some of these grades, especially the Gen 3s?
Our experience as a tool maker is that we always want our customer to provide us the material card that they want us to use to do the simulations. First of all, we want to use the same card that they're using as they evaluate the product, but also they're able to get the cards from the material supplier, who often will not give them out to anybody other than their customer. And so they get the cards, they provide them to us to use in the simulations. We've done a tremendous amount of evaluation of generic cards from libraries or wherever against specific material cards from manufacturers. And there's a significant benefit to using manufacturer's card with the more advanced materials.
Because those new cards capture the failure modes associated with the new grades.
Yeah, because I think all of the advanced steel producers, especially the Gen 3 materials, are undergoing a lot of characterization work by the mills as they're released, and they're doing a lot of work that hasn't traditionally been done in order to make sure that they've got the best possible cards for their customers.
Eren, you want to add any last comments since you're our guest speaker on simulation next week?
Yeah, of course. About material cards, I made a presentation a couple months ago in Great Designs in Steel. And what I believe is there are several aspects you have to be focusing on. A full material card may be too much time consuming and costly. We just did it recently to an OEM. They didn't have any risk of splits, but the spring back was totally out of what they were expecting. So what we did was only the kinematic hardening part, and it solved the problem. In another one, there were both splits and spring back problems. So you have to understand what the problem is, or as the die designer, Mike should tell me what are they expecting as a problem, and we should focus on those parameters. And also friction, lubrication conditions has to be modeled. And that's a lot of experimental work that we are doing, but I would like to explain them in detail in the next week's webinar, hopefully.
More on that next week. All right, outstanding. We're a little bit over. We apologize for keeping you over, but gentlemen, you guys did a really great job today. So thank you so much for really an outstanding and interesting session. I hope everybody found it to be of value. To our audience, thank you for attending today's program. We hope you found it to be valuable. And I again want to thank our sponsors as well for supporting the program. I want to remind everybody that an archive of the event will be available up on our website soon. You'll receive an email from us when that is the case. And I don't know, Danny, hopefully you'll make your PowerPoint presentation available to everybody as well. Please remember again to join us next Wednesday for session 2 of MetalForming Live. As we discussed, our panel will focus on progressive die design and simulation. So if you're not already signed up for that event next week, please visit our website, metalformingmagazine.com, and register. And finally, I want to thank Lou and our fine production team for all their efforts making this event such a success. Our event planner, Ali Miller, marketing manager, Drew Gutierrez, art director, Nikki Formica, our cameraman, Christian Pokrivka, and last but not least, our producer and director, Randy Kish. Everybody did an outstanding job in making this a really successful event. So that's a wrap. We'll see everybody next week. You can close your browsers now and wish everybody a great afternoon.
Delmia Works runs this company that allows you to analyze where you are, see where you're going, and figure out what the path is that's going to get you there. Every step of the way through your production process is driving into the balance sheet and the profit and loss.
Delmia Works has helped us provide all the team members here, all the individuals within the business, with the best tools to give them the best chance to do the best job they can.